Then let go.
G'day everyone and welcome to another video here. We're in a new topic now with our course. So we're doing sequences and then we move on to series. Sequence and series for most students at a methods level, they don't find it too difficult, but there are little tricks and things in there as well. So keep a listen on to this one. We're going to run through two of the main series that we do. Then I'll rub out these numbers and I'll do another one for you as well, just to see that we've got the hang of this. So two different types of sequences we have. We've got geometric and we've got arithmetic. Now, you either call them a geometric sequence, which is no problem, or a geometric progression. Similarly, arithmetic sequence, arithmetic progression. You'll hear both of those terms coming through. So what's the difference between geometric and arithmetic? Let's work with geometric. Geometric is a constant multiplier. All right? So it links in very closely to exponential equations. Okay? So we're multiplying by the same thing each time. So here you'll see with this set of numbers that as I move to the next one, I'm multiplying each one by 2 to get the next one. So here to here, I'm multiplying by 2. Here to here, I'm multiplying by 2, onwards all the way through the sequence, and that would continue on. Maybe I should actually put a ... and ... because it will carry on forever. Now this number here we call the R number, R for ratio. And how do we work that out? We work out R by saying Tn plus 1 divided by Tn. So what's that telling us? Now remember that T is a term. Okay? So T1 is this one right here. It's the first term in the sequence. T3 is 20. Tn plus 1 is the next term. Let me put this in a more practical context. Let me say n is equal to 2. So this would be equal to T2 plus 1 divided by T2, which you would see would be equal to T3 divided by T2. So all this is really saying, it's saying take the next term and divide it by the current one. So that's taking that one and dividing it by that. Taking that one and dividing by that. That one dividing by that, and you notice that each one of those come out as 2, which is my constant multiplier. So the ratio is the constant multiplier. It's the thing that I need to do to get to the next term. How do I work that out when I'm not given it? This little formula will do that for us. Okay? So this here, R is equal to 2, a common ratio. Why do we need to know that? Well, we need to know that down here. But we also need to know one other piece of information from sequences generally. We've got our ratio, we also have the first term. So we actually call T1, A. We give that a little name. So I'll just write it up here. T1 equals A. So in our formulas you'll see some A's jumping through. That's just saying T1. We could write T1 instead. We generally write A. What do we got to do now? We've got to write two different formulas for a geometric sequence. Let's explain it. The first one here is going to be a recursive formula. A recursive formula. So a recursive formula refers to the term before. All right, and we'll get to that in a minute. The second one is a non-recursive formula where it doesn't refer to the term before. Okay? Let's dive in a bit deeper. See this one, Tn plus 1. That's saying the next term. So to work out the next term, I look at the current term, and then I'm going to add, actually no, let me change this, I made a mistake here. Oh, that's not good. I should have done this, did it correct over there. Okay, that's better, that's better. So to get the next term, I'm going to take the current term, and I'm going to do something with it. Well, I'm multiplying by 2 each time. So the thing that would go in here is going to be, color-coded, is going to be the 2. Because to get to the next term, I take the current term and multiply by 2. All right, and I'll move this across a little bit. Now, when I do a recursive formula, I've also got to give a starting term. Because this is telling me how to get to the next term, but it doesn't tell me where to start. And of course, it's good knowing that I double it each time. Do I start at 7 or 10 or 9 or 3 or -2? I don't know where to start. So I've got to give a starting term. Normally we give T1, so in this case it would be T1 equals 5. Normally we give T1 equals 5, but you don't have to. You could give T2, T3, T4, any T value you like. All right? Normally this is what's given. So a recursive formula refers to the term before and tells you what to do with it and gives you a starting term. A non-recursive formula, we use this formula here. Now what I want to do is I want to explain this part right here. AR to the n minus 1. All right, let's pick two T values. I'm going to pick this one right here, and I'm going to pick this one right here. Now between those two values, between the 5 and the 40, each time I'm moving along my sequence, I'm multiplying by 2. So I multiply once, twice, 3 times. I make 3 jumps. I multiply 3 times, but I'm getting to the 4th term. So the number of jumps is 1 less than the term number I'm going to. Hence why I've got n minus 1, because 4 minus 1 will tell me the number of jumps that I need to do. So that's why that is n minus 1. It's r raised to that power because each time it's times by 2, times by 2, times by 2. So that part of it really breaks down to 2 to the power of 3. 2 to the power of 3. The 3 being how many jumps I moved, and the 2 being the multiplication each jump. Now I've also got A here because I started here, didn't I? T1, remember T1 is A? I started here and this is what I did to get from here to here. So this would be 5 times 2 to the power of 3. Right? But as a general formula, we would write it like this. We would write 5 times 2 to the power of n minus 1. I wouldn't fill this part in. That was just one example. Because then if I wanted to know T5 or T8 or T12, then I'd put 12 in here on the left-hand side, and I'd put 12 in here, and calculate. So this is a general formula, a non-recursive formula. This is a recursive formula for finding future terms. Fair question now might be, why have 2? Why not just go with 1? Well, this recursive formula is great if you only just want to skip along a couple of numbers. Maybe you're at T5, you want to get to T8, pretty easy to do. If you want to go from T5 to T74, with this formula, you'd have to work out T6, T7, T8, T9, T10, all the way up till you get to T74. Way too much, way too much. That's where this comes in handy. Okay, this comes in handy because we can just jump straight to it. I explained to my students the other day to kind of see this, is that a recursive formula is like climbing a ladder. You've got to start on the first rung, and then the second, and then the third, and then the fourth, and you climb your way up. But if you get in an elevator or a lift, you just hit the button and you go straight to floor 17, straight to the 20th floor, whatever it is. So this one will get you straight there. This one you've got to go rung by rung. Maybe this is like the stairs. You've got to go level by level. This is the lift, straight there. Sometimes one's handy, sometimes the other's handy. That's our geometric sequence. Real quick revision here. Geometric sequence. Constant multiplier. That constant multiplier we call R. We have the first term equaling A. That's just what we use. And we have 2 formulas, recursive and non-recursive. Recursive refers to the term before, must give a starting term. Non-recursive, this formula, get some numbers in, we end up here. Now one last point, be really careful. This is not right. No good, don't do it. You can't multiply these two together because BIMDAS would say brackets, indices, I've got to do that part first, and then multiply by 5. This is no good. Don't fall into that trap. Don't do that one. Don't do that one. Geometric here. Lots and lots of stuff there. Let's dive over to arithmetic now. Hopefully with a bit of work from there, you look here and you say, well, I can kind of see something going on here. An arithmetic sequence or an AP, what we're doing is instead of multiplying, we're adding. So you see there's a plus 2, plus 2, plus 2 all the way. How would I work that out if it's not going to jump at me straight away? Well, it's similar to this, but it's a little different. It's that d, the constant difference, equals tn plus 1, the next term, minus tn, the current one. Let's look at it. 19 minus 17, 2. 21 minus 19, 2. 15 minus 13, 2. Easy. So that's what we work out for d. And you see this creeping through here. This is our recursive, same as over here. I'll put a little r next to it. This is our recursive. So we're saying the next term is equal to the current term. Well, we've just got to add the difference on. It's really add the difference. The difference here is 2. So that's our formula there. So here we were multiplying by 2. Here we're adding 2. Obviously 2 doesn't have to be the same number of both, but in this case it is. Got to give a starting term. T1 is equal to 13. Done. There's my recursive formula for an arithmetic sequence. Our non-recursive here. Let's talk about this n minus 1. Very, very similar to over here. If I was going to go from this term here to this term here, I'm making 1, 2, 3 jumps. Same as what I did over here. Now, that would mean I'd kind of be working out T4. This is saying the first term, so that's really like my 13, plus n minus 1. Well, n minus 1 is 4 minus 1, which would be 3. That's telling me how many jumps I'm making, and each jump is the difference, which would be 2. So this is telling me how many jumps, this is telling me how far each jump is, and the number of jumps is 1 less than the term number I'm working out. So this here, we can expand this and play around. You know how I said don't do this, this is bad? We can here, because this is just BIMDAS. This is going to, oh actually wait on, this is a particular example. Let me do a general example for you and I'll multiply it out. So if I multiply this out, wouldn't it be this times this times this? So we'd get A plus ND minus D. Now when we do a practical example, I will in a moment, A and D, whatever those numbers are, we can just throw them together. So let's do a practical example. I'll squeeze it in here again. So let's do this one. Let's go and say Tn equals, now I'm going to fill in numbers for A and D. I'm not going to fill in N because I want it to be usable anyway. A is 13 plus N minus 1 times 2 in this case. Multiply this out as I said above. 13 plus 2n minus 2. So isn't that going to be equal to 11 plus 2n? And let's just check. This is the way. Take 4, put it in. Put a 4 in there. 4 times 2 is 8, plus 11 is 19. Bingo. Got it. So this is our non-recursive here. So, real quick recap. Arithmetic, constant addition or constant subtraction. That's the same thing really, you're just adding a negative number. We can work out our difference. We can write a recursive formula, remembering that we need a starting term, and a non-recursive formula, and we can do a bit of a tidy up here. You don't have to, but we can do a little bit of a tidy up here. Okay, let's do a rule. I haven't got room here. I'll do another video later with a couple of examples, but I think this has got you pretty well sorted for arithmetic and geometric sequences. Once you get past this, we'll move into arithmetic and geometric series, which are summing up all the terms. Rather than just individual terms, we start summing them all up. And then there's one more trick later on from that, and that is sum to infinity, which is when you have a convergent geometric series. But we'll get to them later. Thanks very much, everyone. Hope that helped you.
What does this one do? How do I zoom in? Oh.